Hey class, today we are going to look at SHiFT, a semi-hosted framework for fuzzing applications running on embedded devices. It is based on the paper that was published in the 33rd USENIX Security Conference by researchers from Northeastern University and Florida International University. Today, embedded devices are ubiquitous. They can be found from everywhere from military asset tracking and remote patient monitoring to edge computing enabled wearables and self-driving cars. As this chart illustrates, it is projected to become a trillion-dollar industry in the next 4 years. In 2025, IoT devices collectively held 79 zettabytes of data, underscoring the accelerating scale of information generated and stored across embedded devices. Embedded computing research has led to very powerful and energy-efficient IoT architectures, enabling edge computing and smart home applications, which implies that any vulnerability in these devices can be a threat to society at large, as well as at an individual level. Moreover, these devices are a treasure trove of sensitive information. In the recent years, escalation of these vulnerabilities to large-scale attacks demonstrates the importance of testing embedded and IoT applications for vulnerabilities and bugs before deployment. So, to solve this challenge, uh, researchers have developed fuzz testing. The term fuzzing was introduced in 1988 by Barton Miller at the University of Wisconsin-Madison as part of a class project. The project was designed to test reliability of Unix command line programs by executing a large number of random inputs in quick succession until they crashed. Miller's team was able to crash 25 to 33% of the utilities that they tested. They then debugged each of the crashes to determine the cause and categorized each detected failure. In the 1990s, fuzzing mainly involved random input generation without understanding program structure. While primitive, these early dumb black box fuzzers were surprisingly effective at uncovering crashes, buffer overflows, and input validation bugs. From 2000 onwards, fuzz testing evolved into more sophisticated forms such as mutation-based, generation-based, and coverage-guided fuzzing. Tools like AFL use runtime fuzz feedback to systematically explore program paths, making fuzzing a core technique in modern software security and testing pipelines. Today, fuzzing is an automated software testing technique which works by supplying a system under test with random unexpected inputs and monitoring it for any unexpected outcomes or scenarios. These unexpected outcomes or scenarios vary with the system under test and the goal of the fuzzing user. The fundamental building blocks of a mutation-based coverage-guided gray box fuzzer look as follows. A seed pool consisting of initial set of inputs to mutate off of. These inputs are generally selected for their good semantics and coverage increasing properties, so the fuzzer does not waste initial time generating random inputs that get rejected immediately. Next, we have a seed scheduling algorithm which decides how seeds are selected. This can be random. Then once the seed is picked, the mutation engine, which mutates this seed, uh, it can use various strategies like random mutation, bit flips, byte flips, slicing, etc. Uh, then the next component is the target binary, which is instrumented with coverage tracing and fault detection runtime hooks. The mutated input is provided to the instrumentation binary. The program executes and returns coverage feedback, which dictates which inputs are interesting and which can be discarded. On detection of a bug or a crash, the input is saved for later triaging. However, it is not straightforward adapting this fuzzing loop to embedded applications for the following reasons. Embedded devices have limited memory and computational resources to store the seed pool, perform mutations, and coverage analysis, which form the core of the fuzzing loop. Embedded architectures are diverse and differ from device to device. Moreover, operating system support is also highly dependent on the platform. In many cases, the embedded device does not even possess any operating system, running firmware on bare metal. These minimalistic designs, as such, do not possess the facilities required by fuzzing that we take for granted in a desktop environment. To solve this challenge, early works proposed rehosting the embedded applications on a more powerful desktop. In this setting, the microcontroller hardware is emulated on the workstation through sophisticated techniques. As such, both the fuzzing and execution of the target binary happens on the desktop device. Some later works extend this idea to add the MCU hardware in the fuzzing loop, where certain parts of the firmware that interact with the hardware are hooked and executed on the actual MCU while executing other parts on the workstation emulator. Again, in this case, the fuzzing happens on the workstation. However, this approach to fuzz testing embedded applications has some obvious pitfalls. Rehosting based on software emulation inevitably approximates the behavior of real hardware at its best. This approximation compromises the fidelity of the firmware-hardware interactions and precludes the identification of firmware issues that are closely associated with hardware behavior. Secondly, the fault detection techniques of current rehosted solutions are based on experimental-only methods, which require considerable engineering effort or only provide coarse-grained detection capabilities. Even if rehosting techniques might provide synthetically good coverage over time, they are limited in detecting specific faults when they occur. Finally, software emulation lacks compatibility with complex peripherals and DMA, whereas hardware-in-loop solutions often require custom hardware only available for academic use. To solve these challenges in rehosting frameworks, SHiFT proposes semi-hosting. Semi-hosting is an extension of hardware in the loop, which lets go of the emulator. In this framework, the execution of the target binary happens natively in the MCU, while the bulk of the fuzzing duties are done on the more powerful workstation. As such, the workstation now does not have to approximate the behavior of the hardware while observing real-time effects of complex interactions with the MCU peripherals. The fuzzing loop proposed by SHiFT based on the semi-hosted approach now looks something like this. The workstation stores the seed pool and performs input generation, which includes seed scheduling and mutations. The mutated input is then sent via a serial port proxy to the MCU using the USB CDC communication protocol. This serial proxy also stands in for the target binary while the feedback is received from the MCU. The MCU consists of two separate tasks. One is the monitor task, which interacts with the second instrumented target task. The monitor task injects the input to the target tasks, implements the mode of execution, as well as performs fault handling duties. Finally, the coverage feedback, as well as any detected anomalies, are forwarded by the monitor task to the serial proxy for further analysis. The workstation takes this feedback and generates the next input, and the process repeats itself. Since the design of SHiFT requires a monitor task and a target task, it has two available configurations depending on the number of cores available in the MCU cluster. When only one MCU core is available, SHiFT leverages FreeRTOS to schedule the monitor and target tasks depending on the execution mode. In the standard mode, FreeRTOS monitor task creates, deletes, and recreates target tasks. In the persistent mode, FreeRTOS monitor task reuses the target task. When two cores are available, SHiFT uses the dual core configuration. This configuration, unlike single-core configuration, can also support bare metal firmware fuzzing besides FreeRTOS-based applications. The idea in this configuration is the same as single-core configuration. The tasks are now simply executed as independent firmware on separate cores. In the standard mode now, instead of deleting and recreating target tasks, monitor core simply reboots the target core. For coverage tracing, SHiFT uses the sanitizer coverage or SANCOV hooks provided by the GCC compiler. GCC automatically adds hooks at the end of each basic block and provides the program counter address of the basic block that was hit. SHiFT runtime leverages these hooks to calculate the edge coverage and stores the results in AFL-style bitmaps. These bitmaps are reduced in size to fit the memory constraints of embedded devices. In order to reduce the time wasted in communicating these bitmaps back to the workstation for analysis, SHiFT opts to only send the exercised edges and their hit counts to reduce the communication delays. The workstation updates these edges in its local copy of the bitmap and performs analysis, which it then uses to generate the next input. For fault handling, SHiFT leverages a couple of different facilities available on embedded devices. For example, if the embedded device has a memory protection unit, it uses the memory protection unit's out of bounds and privilege mismatch detection capability. For ARM Cortex-M architectures, it uses the inbuilt traps for integer divide by zero and unaligned accesses. For embedded devices with the floating point unit, it uses the FPU's divide by zero and invalid floating point operation detection capabilities. To detect hangs, it uses FreeRTOS primitives when in single core configuration and the watchdog timer for dual core configurations. Uh, then it uses it detects exceptions via exit codes. These exit codes are provided by the handler when the execution returns. Finally, they also use address sanitizer hooks provided again by the GCC compiler, which they use to detect memory-related error detection. To evaluate the impact of semi-hosting on fidelity, SHiFT uses a two-dimension qualitative analysis. Memory fidelity ranges from complete black box down to register level fidelity. Execution fidelity ranges from black box to functions to basic blocks to instructions to cycle accurate fidelity. Based on this analysis, SHiFT along with some other semi-hosting frameworks such as MuAFL and GDB Fuzz, surpass all emulation-based solutions as shown in the figure. To evaluate the performance of SHiFT in terms of fault detection capabilities and runs per second, SHiFT's authors use a custom benchmark. This benchmark consists of different conditionals such as hang or seg or null, which will be satisfied based on the inputted string. So if the input string matches one of these conditional keywords, the program execution will go inside this conditional. Inside each conditional is a different type of buggy code. For example, a never-ending while loop, hang, uh, segmentation fault, or a null dereference. So there are 15 total bugs synthetically planted in this benchmark by the authors, and they use this benchmark to test the fault detection capabilities of SHiFT and compare it with related works. Based on this synthetic benchmark, SHiFT, as this table shows, detects all the 15 bugs planted in the benchmark, which they claim no other related work could do. When it comes to executions per second, SHiFT in single core and standard mode configuration performs relatively similar or even better than running the benchmark natively on the workstation using AFL++. This is because of the overhead of process creation on an operating system, like a full-blown Linux operating system, versus the lightweight task creation on FreeRTOS. However, as expected, native workstation execution using FL++ surpasses SHiFT in the persistent mode of execution. Now, it must be noted that these performance metrics are done on the synthetic benchmark and not real firmware, so their validity in the real world might be contested. The paper further evaluates SHiFT using real-world firmware from common embedded applications. As seen here, SHiFT has a mixed basic block coverage over time compared to software emulation techniques. The authors explain this behavior, claiming that software emulation techniques synthetically boost coverage due to their low fidelity. But this low fidelity also implies that even with a better coverage, they cannot always find more bugs than semi-hosting techniques. To prove this, they compare false positive rates and true positive rates of fuzzing each benchmark using the various techniques. As seen here, SHiFT has no false positives for the given benchmark suite, and not only does it discover all the previously discovered vulnerabilities by related works, but it also uncovers 5 previously unknown vulnerabilities. This is because semi-hosting enables detection of faults emerging from interactions with peripherals, as demonstrated by Shelley-Dimmer benchmark. Moreover, running the binary natively on the MCU allows discovery of bare metal and post-silicon bugs which can be missed in software emulation. Moreover, SHiFT at its best is 100 times faster than software emulation techniques at discovering the same vulnerabilities. Based on these results, do you believe that SHiFT can replace software emulation? Not really, as software emulation is well known for its independence from the physical platform, which in turn facilitates advanced analysis with much flexibility and scalability. While semi-hosting provides higher fidelity, it is not as scalable as software emulation. As such, both semi-hosting fuzz testing and software emulation are complementary methods. Okay, what precautions should be taken for fuzz testing on hardware? Well, fuzz testing, due to its nature, stresses the hardware, can damage the system, or force it into unsafe states. Therefore, the tester has to implement mitigations, for example, to prevent wearing out the MCU's flash by repetitive writing operations, or avoid testing devices connected to physical actuators that can behave unsafely. Okay, now what are some shortcomings of semi-hosted fuzzing in the style of design presented by Shiv? Firstly, communication is a bottleneck and introduces large delays in fuzzing speeds. Shift uses a high-speed USB-C DC bus, but again, many embedded devices lack such sophisticated communication protocols. Secondly, Shift's design requires two tasks to fuzz a binary. This compels use of free RTOS for task scheduling, preventing bare metal application testing. While dual-core configuration allows bare metal testing, it is significantly less performant than the single-core configuration. Most embedded devices do not possess multiple cores to increase the performance. And thirdly, while this was not mentioned in the presentation, the AFL style bitmaps that they store in on the MCU, that is on the device, are upwards of hundreds of kilobytes in size. They're 100 to 250 kilobytes in size. And while this works for a lot of embedded devices, a lot of embedded devices do not possess even this amount of storage. Their RAMs could be as small as 32 kilobytes or even 8 kilobytes. So again, Shift won't be compatible with such embedded devices. Finally, based on this discussion, I want to leave you with a question. Given the shortcomings of Shift, what would you do differently to improve the semi-hosting fuzzing framework? In summary, Shift shows that fuzz testing embedded applications requires a method that considers the resource constraints, diversity of software and hardware, as well as bare metal nature of embedded devices. Shift proposes a semi-hosted framework that enables native execution of target binaries on the MCU, achieving high fidelity of hardware, observability of faults, and compatibility with peripherals. As such, semi-hosting provides a useful alternative to identify vulnerabilities in realistic settings that most emulation-based frameworks seem to miss. Thanks for tuning in.